Yes. Hello, everyone.
Hello.
Can you hear me?
Yeah, please go
Hello.
ahead. It's your presentation.
Yes.
Yes, we are able to see your slides. Please
Okay.
go ahead.
So, hello, everyone. First, I'd like to quickly introduce myself. My name's Ayyoub Frifra. I'm a PhD student at Nantes University in France, and my research project is about assessing and predicting coastal hazards in Western France using artificial intelligence. So it is my pleasure to be here with you today and to have the opportunity to participate and present in this conference. I would like to thank the organizers and all other presenters for making this valuable opportunity available to all of us. It was a perfect mix of topics, people, science, and social gathering. So my presentation today will be about enhancing extratropical storm prediction with artificial intelligence. And my talk this evening can be divided into four main sections. First, we'll see a brief introduction about the project, then the materials and methods used, which contains three subparts: study area, data used, and methodology adopted. After that, I'll share with you the results obtained, especially the prediction of storm characteristics and prediction of storms. And finally, we'll finish with the conclusion section. So the research problem concerns storms, or more particularly extreme extratropical cyclone events, which represent a major risk that can cause damage, serious social disturbance, and loss of a human life. Each year, these events result in loss of life and economic losses due to the destruction of vital infrastructures, in addition to the flood damage caused by these storms. And in the current context of climate change associated with the increase in urbanization, these storms are likely to become more extreme and frequent, which highlights the need for predicting these extreme events in order to mitigate their terrible consequences. And that brings us to the project objective, which is proposing a new approach or a new data-driven approach that uses artificial intelligence in order to predict storm occurrence and characteristics. So now we move on to the materials and methods used in this study, and we'll start with the study area of the project. So the study area consists of the western coasts of France, which comprises four regions: Normandy, Brittany, Pays de la Loire, and Nouvelle-Aquitaine. These regions are particularly concerned by these events because they have already been affected by storms, resulting in many material and human losses. And there are two types of storms that affect directly the study area. The first one relates to storms generated from depressions over the British Isles. These storms pass through Brittany and have a west to east trajectory, and they are represented in the figure right here with an arrow in red color. And then the second class of storms relates to those generated from depressions over the Bay of Biscay. So the second path, which is represented in the figure with an arrow in green. This second path is more extensive with a southwest-northeast trajectory, and it affects a large part of the French Atlantic coast. And for the data used in this project, it was combined from a storm database and buoy data from 1996 until 2020. So the storm database was obtained from the website Meteo France, which contains all the storm events that have occurred in the study area. And the storm occurrence, as you can see in this table, it follows a binomial probability distribution. We take the value 1 if there's a storm and takes the value 0 if there's no storm. And then the historical hourly records of temperature, humidity, wind speed, pressure, wave height, and wave period from the 1st January 1996 until the end of December 2020 were obtained from the offshore buoy data. And then this hourly record were transformed into daily values by calculating the average value for each day, then added to the storm's names and occurrence extracted from the storm database. So the combination of the storm database and the buoy data provided a multivariate time series data that represents a day-by-day record of historical weather and marine data, in addition to the precise days on which storms occurred, which will help us to predict storm occurrence and characteristics and their different characteristics. Now let's delve a little more deeply into the methodology adopted. So to achieve the study objectives, we have followed four main steps. First is data collection. So a storm database or the data was combined using a storm database and buoy data in order to create the final time series data used in this project. Then we have data pre-processing, uh, which uh, which is a crucial step that aims to prepare the data for the implementation of the algorithms. It includes dealing with missing values by replacing the missing value with the mean value of all the data, and then preparing the necessary input shape for each model. And after that, the data was split into training and testing sets at a ratio of 80 to 20. So 80% was used for training the models, and then the last 20% was used for testing the model performance. After that, the third step is data processing. So the research roadmap involved two methods, LSTM, long short-term memory model, and XGBoost or extreme gradient boosting model. The LSTM model was designed to predict the different characteristics of storms, and then the XGBoost model was used to predict storm occurrence based in their characteristics. And finally, the last step is performance evaluation. So the LSTM model used for predicting storm characteristics was evaluated using 5 evaluation metrics, which are mean absolute error, mean absolute percentage error, root mean square error, coefficient of determination, and Pearson correlation coefficient. Then the XGBoost model, on the other hand, was evaluated using various evaluation metrics, which are extracted from the confusion matrix, in addition to the ROC curve. Now we'll see the results obtained in this study, and we'll start with the prediction of storm characteristics. So as I said previously, the model or the data was split into training and testing at a ratio of 80 to 20. 80% used for training and 20% used for testing the model performance. And so the trained LSTM model was used to predict the unseen test period from January 2016 to December 2020. And this figure right here shows the LSTM or the results obtained by the LSTM model for the prediction of wave conditions during the test period. So as you can see, the model provides a good representation of the observed values, as the actual and the predicted curves roughly correspond. So as you can see, the actual values are represented by a curve in blue color and the predicted results in orange color. So we can that, as I said, that the model provides good results and follows the actual values during all the test period. However, we can also observe a little underestimation of storm characteristics during storm values. If you can see the values at the storm events, we can see a little underestimation or underprediction of the storm characteristics. Now here this table, or the first table right here, shows the real and the predicted values of wave height and wave period during storm events. And as you can see, the predictions shows a tendency to be under-predicted during storm events, especially for wave height. And as you can see in the second table, it shows the prediction errors for the LSTM model. So the predictions were reasonable with mean absolute error values of 0.62 and 0.64 for wave height and wave period respectively. Root mean squared error values of 0.86 and 0.81. The high mean absolute percentage error of 24% in wave height shows considerably relative error, demonstrating the underestimation of the model in wave height prediction. And finally, for the coefficient of determination and Pearson correlation coefficient values, the values obtained shows a high predictive association with the actual values. Now we'll see the prediction of other storms characteristics, and especially when we'll see the prediction of the temperature, humidity, wind speed, and pressure during the test period. So as you can see, the model has performed very well over all the unseen test period, but also here we can see that there is some underestimation of storm characteristics during storm events. So this underprediction and estimation of storm characteristics can be explained by the low frequency of storms because storm events represent only 0.7% of the total data used in this study. So most of the available data covers lower character values, which corresponds to non-storm events. So in order to improve further the accuracy of the LSTM model and to overcome this underestimation problem, we should add more storm observation values in the training dataset used for the LSTM model. Now we move on and to the second part of this project, which aims to predict storm occurrence based on their characteristics. So in this part, the goal is to predict storm occurrence, and the target variable here is to predict storm occurrence or the precise days of storms, which, as I said previously, follows a binomial probability distribution, where you take the value 1 if there's a storm and the value 0 if there's no storm. So the trained XGBoost model was used to predict storm occurrence during this test period. And as you can see in this figure, there were 5 storms during the test period. We have Storm Zeus, Storm Eleanor, storm on December 2019, and Storm Kiara, and finally Storm Bella, which is a 2-day storm. So we will consider like that we have 6 storms instead of 5 because Storm Bella lasted for 2 days. And as you can see, the actual storms are represented by light blue points and the predicted storms with light orange points. And we can see that the model performed very well. We can see that the predicted storms concur precisely with the actual storms, which means that the model or the XGBoost classifier developed was able to predict all the storm events during the test period. And here, this figure, it shows the confusion matrix of the XGBoost model. So the confusion matrix is a table that is used to measure the performance for machine learning classification algorithms. And as you can see, the model performed very well. So the number of correctly predicted samples is 6 in the storm class and 1821 in the no storm class. But the most important parameter here in this confusion matrix is the false negatives, which means the storms that were predicted as no storms. And as you can see in this figure, the false negatives or the storms that were predicted as no storms is equal to 0, suggesting that the XGBoost classifier developed is performing very well and having very high accuracy. We have used it also for assessment matrix in order to be more specific and to assess accurately the accuracy of our developed model. So we have used it for evaluation matrix, which are recall specificity, false positive rate, and false negative rates, which can be extracted from the confusion matrix and can be calculated using the following equations, as you can see here. So TP or true positives means the storms that were predicted correctly as storms. TN or true negatives represents the no storms that were predicted as no storms. False positives represents the no storms that were predicted as storms. And finally, the false negatives, as I said previously, are the storms that were predicted as no storms. So this table right here that shows the calculation of these parameters, it shows that the model has performed very well and achieved very high accuracy. As you can see, the recall and the specificity, which represent the correctly predicted samples, are equal to 1, whereas the false positive rate and the false negative rates, which represents the incorrectly predicted samples, are equal to 0. We have used also another assessment method, which is the ROC curve, the receiver operating characteristic curve, which is a graphical evaluation method that is used to measure the performance for machine learning classification algorithms. So the ROC curve is not sensitive to imbalanced data, as in our case, and it can assess or diagnostic the capability of binary classifiers and assess their performance. We calculate the area under the curve metric, which is the IUC metric. Usually this metric ranges from 0 to 1, and the perfect model will have an IUC of 1. And as you can see in this figure, our model has an IUC value of 1, suggesting the very high accuracy of our XGBoost classifier developed. So in order to sum up, we will see the main findings and points of our study. So as I said previously, this study focused on the prediction of storm occurrence and characteristics. And in order to do that, we proposed a new approach that is based on the use of artificial intelligence algorithms, especially LSTM and XGBoost. The LSTM model was used to predict the different characteristics of storms, named wave height, wave period, wind speed, pressure, humidity, and temperature. The XGBoost model, on the other hand, was used to identify storm-specific patterns and predict storm occurrence. So it used the characteristics in order to predict the occurrence or the precise days of storm occurrence. So as we have seen that both models have performed very well and produced good generalization ability with unseen data, even though the LSTM models still need more refinement in order to predict the exact values of